This is a talk on architecting distributed cloud applications. I will be your host for the next hour. My name is Jeffrey Richter. I am now an employee of Microsoft. I've been there for about the last 3.5 years now, and I'm a software architect working on Microsoft Azure. I was first on the Service Fabric team for quite some time, and then I switched to the Azure Storage team after that. And what caused me to even produce this talk at all was that as a member of these teams at Microsoft and meeting with customers, it became very clear that the conversations with the customers they didn't go well. Because a lot of customers, they didn't understand exactly what a container was, they didn't understand what a proxy was, they didn't understand what a load balancer did. There was a lot of terms and terminology that would come up in our conversations where we would be talking to potential customers of our services and they really wouldn't understand what the terminology was all about. And they wouldn't understand how these different pieces would fit together. So after I had done that for a couple of years and tried to work with these customers, it dawned on me that it would probably be very useful to go and produce some kind of course on how to architect distributed cloud applications. And I didn't want it to be Azure focused. While I do work at Microsoft on Azure, this presentation is really a technology agnostic presentation. It's not specific to Azure in any way. Because the moment you start doing that, you start losing credibility with customers. They feel like they just want to sell you things. So I'm not here to sell you anything. I am here just to go through a bunch of topics, a terminology and different pieces and how they all fit together. So that's really what this is going to be. A little bit more information about myself. If you're familiar with me at all, it's probably because maybe you've read one of my books. I've written about 18 books over the past several decades. I put 3 of the more recent book covers up here on the slide, the Windows Runtime via C#, the CLR via C#, and Windows via C, C++ are some of my more popular books. Actually, the Windows Runtime book, really, practically nobody bought that book. But yeah, it's Windows 8, I don't know. There was potential there, but it didn't quite seem to make it. But the CLR book has sold very well, and the Windows book has also sold very well. I'm not trying to sell them. No, though, just don't get me wrong. So I've done that. And then I formed a company called Wintellect, and I was the owner of that company for about 18 years. I just sold my ownership of it a couple months ago. It was a consulting and training services company where we also spent a lot of time talking to customers about how to build cloud applications and different components. So I've actually been doing this, probably since at least Azure was born. So it's probably about 10 years now that I've been working in this cloud distributed computing space, but then doing computing and programming well before then. On the far right, a lot of times people ask me, will I write another book? And I think it's unlikely. I never want to say never, but I think it's very unlikely I would ever write another book. It's not a good business model. You don't make a lot of money from books. It takes a lot of time and effort to do it. However, I still do like being able to teach technologies to other people. And so my most recent thing is I have created a 6.5-hour technology agnostic course on architecting distributed cloud applications, and it's available for free on YouTube to anybody. If you go to edX, there's collateral material, and you can pay $100, which I get none of, by the way. And, but then you get a certificate when you're done. So if you're interested in that, feel free to check those out. And I may do more videos in the future. I think that's more of a way for people to learn. I learn a lot by watching videos myself. I usually watch them at double speed. You can go by really fast, double speed. And then at the bottom left, there's ways for you to reach me if you would like to. So there's my email over there. That's my personal email. Then there's LinkedIn. You can befriend me on LinkedIn. And then my Twitter handle all the way at the bottom. OK, so that's it for me. And so now we can start getting into the actual content. So why cloud apps? And you kind of have to look at what we did when building distributed systems in the past and what we're doing to build distributed systems in the present. So if we just take these various topics, like what are the clients that these services are going to be dealing with? Well, in the past, The clients were typically the enterprise or the intranet. That is, the company would go and build this application for themselves. But today, when we build these services, we're building them for the public at large. And so they're available on the internet. That means the scale of them is much, much bigger, right? We have many more people using them. Also, they're used, if it's a worldwide scale, then your service is used throughout the day. Right? If it was, let's say, just for the enterprise and you were based in the United States, then maybe you'd be busy from 9 to 5, and then you wouldn't have much work doing in the evenings. So you tend to be more on all the time and of much higher scale. Which kind of brings us to the second feature, which is the demand. In the past, the demand was kind of stable, and it was a relatively small amount. But now, as I'm saying, we have a much more dynamic scale where it can grow large, it can grow small, and it can change quite dynamically in short periods of time. It used to be that when we were building our distributed applications or our cloud applications, they would run probably in a single tenant data center. But now, or a data center that is for a single tenant. Like some company would go and set up their own data center and they would run their services in that. But today we have data centers that are enormous. You know, Microsoft has 40-some different data centers around the globe, and they're multi-tenant data centers. We have websites in there or services there from company A and company B and company C. And so that means we have to have additional isolation support. We have to have additional security. We have to worry about hostile multi-tenancy, where one service goes into a bunch of infinite loops, but there may be some other company's service running on the same machine. We need to protect them from one another. These are kinds of things we didn't really have to think about in the past. In the past, for operations, like when you have a new version of your service, typically people, which are expensive to employ people, would go around and install. There was one company I worked with in Florida where when the company had a new version of the service, the programmer would come in with the code on a USB stick, the new version, and a security guard would literally walk them through to machine, installing the code on each of the machines. It was incredibly time-consuming and expensive if you think about all the people and what kind of security is that really. The security guard didn't check the bits on the stick, right? Just that you weren't doing anything other than just copying files on. But that's enough of a risk right there. So today we're trying to do much more with automation. We're trying to automate the building of your code, the deployment of your code into the services. When something goes wrong in the code, we have health applications that can check and monitor the health of your application so that they can auto-correct for any kind of problems that are there. So we're investing very heavily in this kind of automation instead of people for doing these kinds of operations. Scale, I've already mentioned. It used to be a few reliable and expensive PCs where companies would spend lots of money for these very reliable machines. But today, with the way that these cloud vendors are going, like Amazon and Microsoft and Google, they're all buying these commodity hardware devices that are very cheap and inexpensive, and they're just putting them into a data center, and they're running your code on it. And the idea here is that because they're cheap, it's inexpensive to you, but also they can fail. And failure is really a big part of my talk here today. One of the distributed applications have been around for a long time, where you have a client talking to a service over a network. But what really makes it cloud-focused is that you are embracing failure. We have these cheap commodity hardware PCs and cheap routers and cheap, infrastructure devices, and they can fail at any time. But you would like your service to be resilient against that failure. And that's what makes it a cloud system as opposed to just a regular distributed system. And I'll be talking much more about that as I go through the conversation with you. So I am talking about failure, right? It was unlikely, but failure is always possible. But in the present, with cloud, failure we consider to be very likely. And we, as software engineers, we take that into account when we are building the software and designing it. Sometimes that makes things that we do easier as software engineers, and sometimes it makes things that we do harder as software engineers. But it does change things a little bit. I'll give examples at the bottom. And then in the old world, machine loss, so let's say a power failure or a network card failure or a hard disk failure, that tended to be catastrophic. And it brought your service down, and your clients could not hit your service until a person went in and corrected for that problem. But in this newer world, we consider machine loss to be normal. It's just not a big deal. And that your data center that you're running in will hopefully find another machine that is working correctly, provision it with your software, bring it up, add it to your cluster, and everything is back to working fine again, and it was all automated with no human intervention. It just is self-healing. We're trying to make your applications be more self-healing. So in order to address this new cloud or embracing failure world, there are certain things that we have to do differently when building cost-effective and failure-resistant solutions. So one example here I give is exception handling. In the past, we would typically in our code, we would say, well, we want to catch all possible exceptions because we do not want our service to go down. If it goes down, then there's downtime and the customer request can't get to us. So instead, if something goes wrong, an exception is thrown, we're going to swallow that exception. Maybe we'll log it so we can fix it later, but we're not going to let our service go down so it can continue handling requests. That's what we would do in the past. But in this new world, this is a thing that I think is easier. If you get an unhandled exception, you can let your program crash, because you're going to be running multiple instances of your program in a cluster, and if one instance goes down, your orchestrator of choice, and I'll be talking more about orchestrators very shortly, your orchestrator of choice is going to restart your application automatically. So you don't have to write the code to catch this and recover, and you don't have to hope that state corruption has not occurred, and that continuing to run with state corruption is certainly a bad thing. Instead, you can let the unhandled exception bring down your application, orchestrator brings it back up, your state is in a known good state again, and now you can continue running. It's a much better place to be, I think. And communication. When we talk about communicating between two machines, in the past, we would say that all the communication is going to happen in order, and we can say that it's going to happen exactly once. But in this new world, where in order to get resiliency, we're going to run our code on multiple machines, and we're going to put a load balancer in front of them. This is a typical topology, but not the only one possible, of course. Then when a client makes a request to a server, it goes through a load balancer. The load balancer picks the machine, and the request can come in out of order. And furthermore, it's possible that a machine will go down because we're embracing failure. We now know that our code, while it may start processing a request, it may crash in the middle. And we would like to be resilient against that. The way we make ourselves resilient is we have the clients do retries. And this is mandatory, in my opinion, is that in this new cloud-based world, clients applications must support retries against the service. It's not an optional thing. And that means that the same request can happen to a service multiple times, or maybe different instances of the same service. And so now the service code has to be written to handle that request idempotently. I'll talk more about this a little bit later on in this discussion too. For some operations, this is actually trivial to make it happen, for things to become idempotent. But for some services, this is actually quite difficult. And you, as a software engineer, would have to do a bunch of work in order to guarantee the idempotency. Anyway, as I said, I will talk more about that a little bit later on in the discussion. So those are just two examples. So as I say, cloud computing is really all about embracing failure. And there are many reasons why a service instance may fail. And I'm using the word fail, but I could also just mean the word stop, right? It just stops running for some reason. So some reasons are, and the developer-related reason is an unhandled exception has occurred. Then your instance, which may have started processing some message request, has now just crashed in the middle of processing that request. Some DevOps reasons is scaling the number of instances down. It could be that during the day you have 100 instances of your service running on 100 different machines, and in the evening you want to scale that down to only 50 instances. Well, at some point, there could be a machine that's running a request, and then the scale down command comes in, and then that machine goes down, and now it's not processing that request anymore. Now, you could try to handle that gracefully and not let the machine go down until it's finished processing that request, or you should just be able to let it go and just let it die instantly, and then that request should be retried, and then one of the remaining machines that are up should be able to handle the request. Some other examples are updating the service code to a new version. You're currently running version 1 on some machine, but you want to upgrade it to version 2. Well, the way that we accomplish that is that we bring down the version 1 code, and then we bring up the version 2 code. So again, the version 1 code could have been processing some request at that moment in time when we bring it down. So now version 2 comes up, the client retries, and now the request can go to version 2 instead of version 1. If it goes to the same machine, or maybe something else if it goes to a different machine. The orchestrator. If you're using a public cloud like Azure, then inside our data centers, we may decide to move your code from running on this machine to running on some other machine. And we reserve the right to do that in our own data centers. So that means that you can come down and we can bring you back up somewhere else. You don't even know that this is happening, except there is some period of downtime where your application instance is not handling requests. Of course, you have multiple instances, so we'll do that one instance at a time. We don't bring it all down and bring it all up. So we'll try to do that slowly so that you don't notice that there's any kind of impact to clients that are accessing your service. And then the force majeure, which is things that are acts of God or out of your control. Hardware failures can happen any time. Power supply issues, a fan can cause overheating to occur. A hard disk crash, a network controller can go out, a router can go bad. Sometimes somebody steps on a network cable and then the network connection is gone inside the data center. All these things are conceivably possible. And then there's other data center outages that can happen, natural disasters, storms, thunderstorms, attacks. They don't like me to say attacks, but it's possible that there can be an attack on a data center. That's why we don't ever publish the full addresses of where our data centers are. We're trying to hide it a little bit to make it harder for people to know. So we say we have a data center in some city and state somewhere or some city around the world, but we don't give the exact address of where they are. So since failure is inevitable and it is unavoidable, embrace it. Right? That's kind of the key word, and that's what makes an application be cloud ready, in my opinion. Right? You are embracing the failure. And so you architect your application assuming that these failures will happen, and you also think cattle, not pets. Who of you are familiar with the term cattle and not pets? Any of you? Oh, okay, quite a few, but also the majority of you are not. So there was some guy at Microsoft who I think coined this term, and he says, for cattle, you never name them. Right? This is not my cow named Jeff, right? And so you have a bunch of cows, and we kill them and eat them, and we don't feel too bad about it, generally speaking. This is probably going politically off the rails right now at this at this moment in time. I think I know the moment where I lost it, but just try to go along with it in theory, all right? Whereas pets, on the other hand, you name them and you love them and you feed them and you bring them to bed with you at night and things like that. And so you don't want to think of your computers as, this is computer, A, B, and C, or, Jeff and Fred and Mary. You don't want to name them, right? You just want to say this is some computer, some computer, some computer, and it's running the code. So that's the mental model to have, is to think cattle and not pets for these things. It doesn't matter which computer is running your code, just as long as some computer is running your code. All right, and then we use an orchestrator that avoids single points of failure. This is another thing you always have to be thinking about, is where is a single point of failure? And if that fails, then has everything gone awry? So you want to try to avoid single points of failure as much as possible. And typically, we solve that problem by running multiple instances of your services. Or if you have data, you replicate the data. So if one hard disk goes out that has your data, you can go to a replica of that data to continue working on the data that's there, etc. Okay, so now on this slide, I'll say that I do have some questions already. I have to remember to sometimes look at this thing. What if a load balancer failed? Does it recover automatically in Azure or other cloud-oriented technologies like Kubernetes? Definitely it does in Azure. In Azure, we have replicas of the load balancers, and so if a load balancer does go out, we have other load balancers that can take over the requests. In Kubernetes, that would depend on the hardware that you're running it on. You can run Kubernetes in a public cloud, like Azure or Amazon, or Google, certainly. But you can also run Kubernetes in your on-premises data center, too, and it would depend on the hardware infrastructure as to whether or not the load balancer is a single point of failure or not. If it's your own data center, that's your responsibility to make sure. If it's in a public cloud, then it's their responsibility to make sure. How many default duplicates of your software are there in the cloud in Azure? How many duplicate defaults of your software? I'm not exactly sure how to interpret the question. I can answer it a couple ways, though. So when you upload your software into a cloud, which actually is what this very much slide is right about. It's a great segue into this slide. Then we in Azure, we will replicate the code that you deliver to us, usually at least 3 times. So we will have it in at least 3 places within a data center. You upload your code to a data center, and Azure, there's like 40-some data centers. So you pick and choose which data centers you want. Then you upload your code to that data center, and we will replicate it within that data center. So we have your code available in the service code repository. That's where we would put it, actually. That's why it's a great segue for this slide. But then the number of machines that are running your code, that's up to you to decide. And most public clouds, they charge you hourly for running this code. So you can do 100 instances of it if you want to, but then we would typically charge you $100, whatever the dollar price is for whatever hardware machine you're getting, for 100 per hour. Right? So you want to scale up and scale down in order to control your costs efficiently. So that is a great segue into this slide. So let's now do the slide. So we have a bunch of as-a-service things. And sometimes people say, well, infrastructure as a service. We've had that. That's probably the longest running one that's been around for over a decade now. Then a relatively newer thing is platform as a service. Microsoft had embraced that very heavily at the very beginning when they created Azure, and then found out that most customers didn't want it. They wanted infrastructure as a service. So now we've embraced that more heavily, and we kind of went backwards. But nowadays, in the more recent past, people want to have containers as a service, or also have functions as a service. All of these things are different variations of what I call an orchestrator, or what we call an orchestrator. And in these public clouds, there's these different varieties of orchestrators, but they all have slight nuances to them, but by and large, they all do the same thing. And what they all do is they manage your cluster's set of PCs or virtual machines, their life cycle. So the creation of these VMs or PCs, the destruction of them, the orchestrator controls the networking so that your machines that are part of your cluster are on a private network so they can go talk to each other, virtual private network. The orchestrator monitors the health of the machines to make sure that the hardware is still functioning correctly, your virtual machine didn't crash, your application is still running within the VM. The orchestrator controls upgrading your code from version 1 to version 2, from version 2 to version 3, and so on. The orchestrators, some of them will do automatic scaling for you. So if there's certain times of day you want to have 100 machines, and certain times of day you want to scale back to 50, or if you want to do it based on, let's say, a queue length of messages in a queue, or you want to do it based on some other hardware utilization, like CPU utilization, and scale up if your CPU utilization goes above 80%, or scale down if it goes below 50%. These are all nuances to these different orchestrators, but conceptually, they're all doing the same thing. So that's controlling scaling, and then deploys and running of your service code. All right, so now this animated slide here is going to try to put all the pieces together. So imagine you're sitting at your desk on the globe here somewhere, and you've written some code, and you would like to run that in some data center. So you need to take your code, and you need to go and upload it into the service code repository that's within your data center of choice. And again, this service code repository does replicate your code so that if it's on one hard disk and the hard disk crashes, we want to be able to still get to your code. So we'll replicate it internally within the data center. Now, You can say to the orchestrator, I would like to go and run this code on 4 different virtual machines or PCs. So some data centers let you run on raw hardware, raw metal, so then it would create PCs for you. And some orchestrators, they put it on virtual machines that are on other PCs that are out there. So it depends on which orchestrator you're using, if you get raw metal PCs or if you get VMs on a PC. So in this case, let's say they've gone and stand up 4 different, we'll just say virtual machines because it's the more common case. And now that service code, then they put them into a virtual network so that the machines that are running your code can all communicate with each other. And then the service code pulls out of the repository, gets copied to the 4 machines, and then it boots up, and now all your code is running. So now we have 4 instances that are available for handling client requests that would come into the data center. And it would be, then the load balancer is usually in front of that, which directs the request to one of these 4 machines. Right, so here's a client request now that's coming in. It would hit that load balancer that I just mentioned, and the load balancer would pick one of the 4 machines to go and handle the request. Now, what I just showed here, let's see it again, because PowerPoint animations are so much fun. Okay. Then in the bottom left corner, the service code, it crashes. See? That's crashing code. Right? That would be like an unhandled exception, if you will. Right? So now we have 3 instances running, not 4. Well, the orchestrator is supposed to automatically detect that. Right? It should automatically detect that. And it should automatically rerun your application, bringing it back to life, and so that you're back up at a scale of 4. Right? And these public cloud systems, they all do this for you now. And so you don't have to hire people to know when something crashed and hit reset or reboot, right? It's all done with automated health systems and automatic restarts. Okay. Also, in this example, let's see it again. Okay. Let's say the whole hardware goes down, right? So now it's not just your program crashed, but if it's Windows, maybe you blue screened. Right? Or for some reason, the physical machine with that VM on it has crashed. Again, the orchestrator should detect this automatically. And when the orchestrator does detect it, it can go and bring up another machine in the data center, copy your code out of the repository onto the new machine, and you're back up and running with 4 instances again. Right? And again, this is all automated. There's nothing you have to do. It just all works. And then furthermore, you might want to scale up, and maybe you want to have 5 instances running your code, in which case you can just give a command, or maybe you've set it up to automatically scale if traffic gets to a certain busy point. And then the orchestrator in the data center can go and find a 5th VM, copy the service code from the repository onto it, bring it up, adds it to the virtual network so that they can all communicate, and now we have 5 instances running. Right, so this is what orchestrators typically do. Right? They manage the life cycle of the virtual machines that are running your code. They make sure they're all part of a network so your machines can talk to each other. They monitor health. They do upgrades, scaling, and so on. Okay. So a question just came in. How does Azure Health Status page work? In my company, I've experienced very often a situation where our smoke tests were failing while Azure Status were all green. It's a good question, and I do not know the answer to that exactly. So I don't know exactly what they're doing there. Then my guess would be is they're looking more at a hardware level than at a software level, like to see if there's hardware failures. That would be easier for them to tell. Okay, and how do I move on? Okay. When do you think we're going to have app service support for Java SE on Linux? All right, now you're getting off the beaten path with these questions. So I'm not on the app service team. I was on the Azure Storage team and the Service Fabric team. And I'm not here to announce anything. In fact, I'm trying to be technology agnostic. So I would almost like to stop even talking about Azure and just talk about things in general. All right, so let's now talk about this, which is today, applications consist of many services. And I put micro in parentheses because a lot of times people throw around the term microservices today. To me, the micro thing is a little, it's kind of reinvigorating something that's been around for a long time. To me, it's like a new fad term, but it doesn't really mean too much it's new. So this slide here shows an architecture of a client request that comes into a data center where it always hits a load balancer, and then the load balancer is directing the request to one of, in this case, 3 machines that are running your code. And that's our website service. So the website is one of our services or microservices, if you will. And then that website might need to make a request to the inventory service, which would be another body of code, and in this case I have 2 instances of that body of code running, and then there is some backing data store that's storing that information. It could be something like SQL or some node to SQL data store, something like that. And then I show a third service at the bottom right, which is the order service. It also has its own backing data store, and then there's 4 instances of the order service up in front. And so now these services can all communicate with each other, and you can bring some down, and you can bring some up, and you can scale them independently of one another. This only has 2 instances now, but if there's a lot of requests for looking up inventory, we could scale it up to 3 or 4, or we could scale it down if we want to. Right? Each service solves a domain-specific problem, and it has exclusive access to its own data store. And that's kind of the definition of a microservice, by the way. So these are all services, and the term microservice means that each service would have its own data store, and the data store wouldn't be accessible to other services. It's a small nuance in the terminology. So I have spent a lot of time, as I say, working at these teams at Microsoft and working with customers. And a question that comes up very frequently is, when should I be using microservices? Where do I divide my code up so that this is a service and this is a separate service? Or should I leave the whole thing as a monolith? And over the years of doing this, I have concluded, at least from my experience, this is true, I have only found 4 reasons to split a monolith into microservices. And these are the 4 reasons. The first reason is you want different bodies of code to be able to scale independently of one another. And this is probably the most important reason. So imagine that you had a photo sharing service where you could take pictures with your phone and you can go and upload them to this website over here. And it has to talk to a thumbnailing service, which when you upload photos, it goes and makes a thumbnail image of those photos so it can show you lots of them on a page, and then maybe you can blow them up and look at the individual picture in full size. Well, at certain times of year, people are uploading a lot of photos. Like in the holiday season, people tend to share photos more, so we might need to scale that up. And if they're uploading photos, then we need more instances of the thumbnail service. So I can go and scale that up and add a couple of instances there. But it could be at certain times of the year, people are looking at photos and they're not uploading photos. If they're not uploading photos, then I don't need the thumbnailing service as much. But I still need the front door, right, the front end, if you will, for the photo sharing service. So in that case, I can go and scale the thumbnailing service down if I want to. Right, so that's one example, and this being able to scale independently because you're paying hourly for these virtual machines that are running this code, it allows you to balance the cost of running the service with the speed of giving replies back to customers who are making requests. You might have very few thumbnailing services, and it'll eventually make thumbnail images of all the photos, but if you only have only 1 instance of it, or 2, it might take a really long time. Whereas if you have 10 instances of it, then it can go and make thumbnail images much more quickly. Okay. Another reason to split up a service into multiple services is because you want to use different technology stacks between the client and the service. So one example is the photo share service could be written in Node.js, but the thumbnailing service itself could be written in .NET or Java on the other side. So that's the second reason. The third reason is you have 2 or more clients of a particular service. So this thumbnailing service, can make thumbnail images for the photo sharing service, but it can also make thumbnail images for a video sharing service. Let's say we upload videos, and then it goes and grabs a frame of the video to make a thumbnail of that. So these 2 different services are capable of using the same thumbnail service. Now, I also put version numbers on here. Right now, everything is version 1. But let's say we want to go and we want to adopt or make a change to the thumbnailing service. So in that case, we could bring it down, and then we could bring up version 2. And I do have a note here at the bottom that backward compatibility absolutely, positively must be maintained. So if you're building like RESTful services, for example, where you communicate over HTTP, it's very, very, very common for each request to include an API version number as part of the request. It's either in an HTTP header or maybe it's a query parameter that comes in. This is certainly true of the Azure Storage team that I'm on. We make new versions of Azure Storage. We're adding new features a couple times a year. And whenever we do that, we put the new features behind a new API version. And sometimes we change behavior of old things as well. But if you pass us an old API version, you will get the old behavior. It'll work exactly the way it did before. And if you pass the new API version in the request, then you will, of course, get the new behavior that we think is better. So we can bring up version 2 here, and the photo share service and video share service that were built using version 1, they can still make requests to version 2 because it's supporting the version 1 semantics and behavior. And then, as I say in parentheses, the clients can adopt the new features at will. So the photo share guy can decide, okay, there's a new feature in version 2, and I would like to adopt that, and then they can go and update their service to use version 2. And then the fourth and last reason that I can think of, and this is the most esoteric of the four, is because you might have conflicting dependencies. So in this example, let's say the photo share service, it uses some shared library version 1, and the thumbnail, right now I'm building this as a monolith. Okay, so let's say I'm building a monolith right now, and I have the photo share service, and it wants to use some shared library version 1, and it also wants to use the thumbnail, but it's all in one process now, it's not client server. And the thumbnail has a dependency on some shared library version 7. Well, depending on the technology stack you're using, you can't load 2 different versions of the same shared library into a single process. You can't do it with Java, you can't do it with .NET. Most programming languages, at least the ones I'm aware of, do not allow you to have 2 different versions of the same shared library in a single program. So, if you need this, you could either decide to update your photo share code, if you're that developer, to version 7, then you're fine. But then, if the thumbnail needs version 8, then you'll have to upgrade to version 8, right? You've tied your versioning stories together very tightly. So another way to go is separate them apart. And then you've turned the monolith into 2 different services, so now the thumbnail service can use version 7, and your photo share service can use the same library but version 1, and everything works perfectly fine because they're not in the same process anymore. So this has been my experience, and these are the 4 reasons why it's interesting to split things up. Otherwise, I discourage splitting things up, and I recommend you keep things in a monolith. It's much simpler. And for reasons that I will be going into as we continue the conversation. Another thing that I'll make mention of is this thing called 12-factor apps, or it's 12-factor services. And there's a website here, and I would encourage you to go and check it out. Very briefly, this is 12 things to consider when building a service. And a lot of people have adopted this. I also strongly believe in it myself. The gist of it, though, is really keep things simple. That's really the gist of it. Don't over-architect your solutions. Just try to keep things simple. So I'll just briefly run through what the factors are so we can get on to other things. Right? But the first one is have a single root repo for all your code, and don't share code with another service. Then you start getting versioning issues and things getting out of whack. Deploy dependent libraries with the service. That is, keep your service completely self-contained, right? So that you know what you're going to be producing. The goal here is that when you build the code that's in your repo, you have this deterministic output. And it's always going to be the same, unless you make changes to the code, but the same code will always build into the same thing. Then you tend to put that into a container, And then the container is always a static image as well. And so everything is always the same. This makes debugging things much, much easier and detecting when something went wrong. Do not put configuration in code. Instead, read it from environment variables. Again, environment variables, very simple. Every system supports environment variables. You can go and create a container and set a bunch of environment variables on it. Your application can go and read them. If you introduce something else, then you're complicating it. Right? Environment variables, they've been around for a long time. This is their purpose. Use them for this. Handle unresponsive service dependencies robustly. This is, imagine that your service is up and running and it needs to talk to some database or some other service. That database or service may not be up. So you have to be able to handle that in a resilient fashion and not just go down. Maybe you're putting messages in a queue until the service comes back up, and then it can go and respond to the elements, the messages that are in the queue at a later time. Or maybe you have to do retries and just keep retrying until eventually that service comes online. Strictly separate your build, release, and run steps. Build is going to build a version of the code and the code repo, and it gathers all the dependencies together. So you have this consistent, self-contained, fully runnable result when you're all done. And then release is you're combining the build with your config settings, your environment variables. You can give that a release ID, which is immutable, right? So you assign that some number. Typically, people use a date and time for this and say, this is my build on this date and time with this configuration. Then you can always go back to it, because maybe some new version breaks something and you want to roll back to an earlier version of something. This gives you that ability to do that. And then run step runs the service in its execution environment. 6, your service is one or more stateless processes and should share nothing with anything else. And the way you'll scale up is you'll just by adding more instances to it, and you'll scale down by removing them. Your service should listen on ports, and you should avoid using things like web hosts. Or again, just keep it simple. Run your executable, have it list on a host for requests. Then you can run it locally at your dev box, and you can debug it very easily, or you can shove it in a container and run it someplace else. And it all just works exactly in the same way. It's very nice. Use processes for isolation and multiple of them for concurrency. Some environments like Node, they require this. Some other things like you do multiple threads, and so it's not strictly mandatory. Your processes can crash and be killed quickly and start fast. This is a thing that historically in Microsoft, I would say we've done a really bad job. But we are now taking this much more seriously, especially with things like functions as a service and containers as a service. So for any of you who may have been ASP.NET developers, ASP.NET would JIT the code at runtime. And so you would get this slower startup, but this faster, steady state. And that's fine if you bring your machine up and it runs for a long period of time. But in this newer world now, where machines are going to scale up and scale down all the time, or be moved, or you're going to go from version 1 to version 2, we're constantly bringing your code down and bringing your code back up. I say constantly, but it's not constantly. Don't be scared that we're killing you and restarting you all the time. So but it's more frequent. And so when a new machine is provisioned, we want to get your code on that machine as fast as possible, and we want to get it up and running and responding to network requests as fast as possible. So we're trying to now tune our runtimes, like the .NET runtime, so it has much faster start time. And we're trying to tune our compilers, like the JIT compiler, so it compiles more quickly. Or maybe it starts interpreting initially, and then it starts compiling code a little bit later on, so that we can get it up and responding to requests in a much shorter period of time. And for you, as a software engineer, when you're writing your applications, you also want them to come up and start responding to requests immediately. So don't have very long, drawn-out initialization phases in your code. Try to get up and running as quick as possible. Okay, and we also want to kill you fast too. This was actually a big problem we had in Service Fabric. Customers would write their Service Fabric app and it would be running, and then the customer would want to upgrade the code from version 1 to version 2. Well, what we did in Service Fabric is when we started your code, we would pass you a cancellation token in .NET. And when we wanted your code to go down, Service Fabric would signal the cancellation token. All your code should see the canceled token and go down immediately so that we can bring version 2 up in its place. What happened, though, is that most customers ignored the cancellation token we passed to them. And because they ignored it, when we wanted their code to go down, it wouldn't go down, and then we couldn't bring up version 2. And customers would call us on the phone constantly and say, I'm trying to do an upgrade, and the upgrade is stuck, Service Fabric doesn't work well. And then we would look into the problem for them and say, well, we've passed you this cancellation token, you completely ignored it. So you're not going down when we're telling you that we want to upgrade you. So it was really their fault, but we hadn't done maybe the best job of explaining what to do. And this has led me to have a new appreciation. This experience has led me to have a new appreciation with cancellation. Cancellation is critically important in a code base. And it must be weaved throughout your entire code base. You might have cancellation token or equivalent in some other language passed to you at the top function. And then as you're calling all kinds of other functions, you must be able to pass that cancellation token all the way down. It is critically important. In .NET, how many of you are .NET developers? Oh, quite a few. Okay, so in .NET, we have this very common pattern where a lot of methods take a cancellation token as the last parameter, and it's a default argument where you don't have to pass it in at all. I think that is so wrong. You have no idea. I think it should have been the first parameter, and it should have been mandatory. Because now somebody writes code and they don't pass that cancellation token in, and then somebody wants to call your method and they can't pass that in, or they could pass it, but then you don't pass it on, and now all hell breaks loose. You can't bring this thing down. You end up paying for the VM longer than you want to. The older version is running longer than you want to. Cancellation is really important in this new world, and it really has to be weaved throughout your code base. Don't take shortcuts on that. Okay, keep the developer environment, the staging, and the production environment similar. Again, this makes debugging easier. You know, if it works here but it doesn't work there, you want to avoid those kinds of situations. Log simply to standard output. Usually in the development environment, you just log to the console window. But if you're in production, you can log it to a file, and then you can archive the file. And then finally, deploy and run administrative scripts as separate processes. All right, I don't want to belabor the 12-factor thing very much, but it is really nice. It's about keeping things simple, and I would encourage you to read more about that if you're unfamiliar with it. Let's see, there have been a few more questions that have been pouring in. What is your take on functions as a service, serverless, when to use it and when not to? I think it's really cool, and it makes things very simple for developers. You don't get to control a lot of your dependencies, so that's the downside of it. But if your code is really, it doesn't have a lot of dependencies that it works on, or some other process that needs to be on the machine, or executable that needs to be on the machine, then it's a very simple, easy way to go and get some code, put it in that source code repository, and then the functions of the service orchestrator can go and create instances and put your code on it. And if it's just copying small DLLs that have functions in them, it can usually get the code on there pretty quick and easy, and start using it right away. What else do we have over here? Yeah, so that question about Service Fabric, I don't think I'll answer it. I think that's a troll right there. I don't know. So there's a lot here. How to manage dependencies and do proper versioning among 10 microservices which are calling each other. So I'm going to talk a little bit about versioning coming up, so I think I'll address that later. So this one I'll address a little bit later on. For a new app service, would you recommend the cloud if the business case is not one with large differences in usage, e.g. many users on holidays? That's more of a business decision than a technical decision. I mean, obviously I work for a cloud vendor, so I might be a little bit cloud biased on that. But the cloud vendors, they give you a ton of stuff that you may not even realize. So if you're in a public cloud, they have all these machines and all this hardware, and they do have people that can walk around and fix hardware and do infrastructure things. So you don't have to have your own people managing any of that. We have in Azure, we do have denial of service detection. So if some monster out there in the world is just hammering your service for some reason, we will detect that, and we will do things that. And we don't normally publicize this or let you know, but we do things along these lines. So there's a lot of stuff that you probably don't think about, many people don't think about, that you're going to get for free, with a public cloud provider. And that stuff improves all the time, right? We have teams of people who are working on networking. We have teams of people who are working on routers, teams of people who are working on storage systems. These people are experts in the industry who are constantly going through and making this stuff better all the time. And using a public cloud, you're benefiting from all of that experience and knowledge that's going into all of this. So I am a fan of public clouds for this reason. It really simplifies a lot of things and automates a lot of things, and you're always running kind of state of the art. Okay, I think I'm going to go back because I'm going to run out of time. When am I over? I have 10 more minutes? Yeah, so I'm going to go back to my slides. And I'll take questions at the end if I have more time. All right, so let's talk about networking communication. There is a well-known document called The 8 Fallacies of Distributed Computing, and I would highly recommend that you seek this out and you look it up too. And then I list the 8 fallacies down here on the slide. Here they're sliding in. Okay. But basically, what it boils down to is you can't trust the network. And so you have to do things like retries in there to make sure that your message is being sent to the service and it gets there accurately. And it also has things like you can't trust the timing of the network. You might make a request, you think you're going to get a reply in 10 milliseconds, but it really takes 5 hours instead. Right? So these are the kinds of things to be thinking about when you're making network requests. So to make these things worse, right, we're going to run multiple service instances of your application. And for service failure, we're going to do this because services might fail, and we want to have another instance that's be able to take over for the failing services. And you might want to scale up and scale things down dynamically. So not only is the network rough, but we're actually bringing up and down one side of what's on the side of the network, right, the service itself. So instances endpoints, they can dynamically change over the service lifetime. This was a problem in Service Fabric where multiple instances each got their own IP address, and then if we brought version 1 down and brought version 2 up, it might be on a different node. It could have a different IP address on it. So if machines were storing IP addresses, the client machines were storing the IP addresses of the service, the IPs were changing dynamically underneath you. And so we had to have a naming service that was part of Service Fabric that was kind of this central repository. And so you could say, well, I'm looking for instance 1 of this service. What's its IP address now? Now I'm looking for instance 10. What's its IP address now? And there's other ways to handle this kind of problem, like with a load balancer that effectively does the same thing. That's a piece of hardware. We did it in Service Fabric with software. But it introduces some brittleness into the system. The moment you get an IP address for a machine, that machine could instantly go down. And now you try to talk to it, and it's just not there anymore. There is no way to atomically get the IP address and talk to the machine in an atomic fashion. That's just physically not possible. So you have to be prepared for failure again, where the instances are not reachable. So ideally, we would like to abstract all this from the client code. Each client wants a single stable endpoint as the face of the dynamically changing service instances endpoints. And I said, as in Service Fabric, we did this with a piece of software, but a lot of times in a public cloud, it's done with hardware with the load balancer. So typically, this is accomplished using hardware, which is the reverse proxy. And every request goes through this reverse proxy, which causes an extra network hop to happen. So you're losing some performance, but you're gaining some simplicity. And then the client can use DNS for well-known static endpoints and talk to it that way. And some examples of reverse proxies are things like web servers, load balancers, API gateways, and so on. So again, I put this slide here because a lot of customers I would talk to, they were unfamiliar with this terminology and how these pieces fit together. So on this slide, I'm just introducing that there's 2 kinds of proxies. There's a forward proxy and there's a reverse proxy. A lot of times when we talk about a forward proxy, we just call it a proxy. We don't call it a forward proxy, just proxy by itself. A forward proxy, or a proxy, is on the same side as the clients. So in other words, whoever owns the clients also owns the forward proxy. So a lot of times companies will set up these proxies inside their enterprise for their own employees, and their employees are making requests to the public internet. And it processes the outgoing requests, and it can do things like content filtering, censoring or translation of data, caching of data, logging, monitoring, client-side anonymization of client requests. These proxies are very powerful. You can use them to do all kinds of things or combinations of these things. On the reverse proxy, that is owned by the company that owns the services. They control it. And it can process the incoming request to the services. So one of the things that I'm talking about now is that it can provide a stable client endpoint over the changing server instance endpoints. So that is, there's one IP address that the clients will talk to, which is really the reverse proxy. And then it knows the IP addresses of all the instances on the far right. And they can go up and they can go down, and you can scale up and scale down and so on. But the reverse proxy knows about all that's happening. The clients don't have to know about it at all. They can just talk to the stable endpoint of the reverse proxy. The reverse proxy can do load balancing. There's level 4 load balancers that can handle UDP as well as TCP traffic. And there's level 7 load balancers that always handle HTTP traffic. And then based on the URL or the content of the HTTP message, they can direct it to specific services. They can do server selection. You can do A/B testing this way. I can stand up version 1 and version 2, and I can tell the load balancer that I want 90% of the traffic to go to version 1 and direct only 10% of the traffic to go to version 2. Then I can see if version 2 is working well. And then slowly over time, I can tell the load balancer to now move 50% of the traffic to version 2, now move 80%, now move 100%, and then I can bring down version 1 if I don't have any more traffic going to it any longer. Right, there's all kinds of things you can do with these. SSL termination, caching, authentication and validation, tenant throttling and billing, some distributed denial of service attacks. Like I say, we do this in Azure for you through our load balancer. We will track this. Okay, so now, kind of putting it all together, we have the globe, and a client request comes into the load balancer or reverse proxy. A load balancer is a type of reverse proxy. The load balancer wants to direct that request to one of the 3 website instances that are running on 3 different virtual machines. So it just picks one, typically at random, and then sends the request. In this case, it shows website number 1. It always does that in this example because it's a slide. In real life, it might go to version number 2 or number 3. Okay, now website number 1, it wants to go and talk to the inventory service. So it might go to some kind of table and say, I want to talk to the inventory service. So what is the reverse proxy inventory service endpoint? So it needs to know the IP address. Once it gets that, it can then go and talk directly to that reverse proxy for the inventory service. And then that reverse proxy or load balancer will then pick one of the 3 at random. And in this case, it's choosing number 3 to make the request to the 3rd instance. So now the inventory service can do what it wants to, and then it can come back. Now, I have a note here. It's impossible to keep the endpoints in sync as a service instances come and go. So client code must be robust against this. And again, this is just talking about retry loops again, right? The retry is absolutely mandatory. It's also possible that a website number 1 could fail before inventory number 3 replies. That's also a possibility, right? Because we're embracing failure, so we're looking at all the failure modes. We call these failure modes, what could fail. So that's possible. So what would happen if website number 1 did crash while this thing was still processing? Well, then it couldn't get the reply back here, and then the customer who's maybe using a browser out on the globe, they wouldn't get the reply either. So now, in order to make this whole thing work, the customer needs to retry. And if they're in a browser, they hit F5. Right? That is the customer's retry, is they hit F5. And then, hopefully, everything has self-healed, and when they hit refresh in the browser, it goes back and works again. Or if this is not a browser app, but it's some other app running on a customer machine, it should have a retry loop in it. So then when it retries, it would go through, everything would have self-healed itself, and then the request would all work the second time through. All right, so now, turning a monolith, oh, I'm really running out of time. I'm out of time. Who works for the conference? How late can I go over? Keep going? Just keep going? All right, until they kick you out? Great. Good. Because I took a nap in the afternoon and I feel a little energetic. Okay, so turning a monolith into a microservice. So what does that mean, right? So what it means is your monolith has code in it that looks like this, where you're calling some method and you're passing in some arguments, and the method's going to return some result back to you. But now what you want to do is you want to split this up into a service. So you want to take the code for method and you're going to put that on another machine. And now, instead of calling this method, you're going to make a network request to the other machine. So let's think about that for a moment. Okay. Well, in order to do this, what are the steps that have to be involved? First thing is, because you're now going to insert the network over this call to this method, you really should define an explicit, programming language agnostic, multi-versioned API contract now. Because now it may not be the same language on both sides anymore. So a lot of times people use Swagger for this, or Open API as it's called now, as a way of defining their contract of what this is going to look like. And you really should do this. You should not take a shortcut. You really should do a formal contract on this. Right? And it should be programming language agnostic, because maybe the service will be written in .NET and the client side will be written in Node or vice versa or something. So you want to make sure that all work. And because you're going to go to this loosely coupled contract now over the wire, you're going to lose certain things. You're going to lose things like IntelliSense. You're going to lose the ability to do refactoring, like if you want to add a parameter to this method. You're going to, or rename the parameter. You're going to lose compile time type safety now. Right? These are things that you're going to lose in order to gain this microservice mechanism. Now it gets worse. Because the parameters that you used to just pass to this method, those parameters now have to be serialized into JSON or XML, or pick whatever protocol you like. And that means memory has to be allocated, the objects have to be walked. In many languages, you typically accomplish this using reflection. Reflection is a slow technology compared to anything that's strongly bound. And so we're allocating memory, and we're going to have to go and build these XML or JSON payloads so we can go and send them over the wire. And then, of course, on the other side, it's going to receive the stuff on the wire, and then it's going to have to deserialize them on the other side, which is also expensive. Then the server side is going to want to send a result back to you. So it's going to have to serialize the results, and then you're going to have to deserialize the result back on this side. So there's a significant amount of memory and CPU overhead that's going in. In fact, when I was on the Service Fabric team, there was one customer, and we profiled their code. 99% of their time was spent in serialization and deserialization. 1% of the time was their program actually doing something useful. Okay. So in effect, you're turning this in-process call into a network request. So as I'm saying, your performance is going to get drastically worse now, and you're going to increase network congestion, and you're going to introduce unpredictable timing of the results. It's unreliable because the network is unreliable. Remember the 8 fallacies of distributed computing. So now your code also needs retry loops. It needs to support timeouts. You might want to introduce circuit breaker mechanisms. You should add cancellation support to this method. The server code must be idempotent now, because if there's retries, you might make the request multiple times, and it has to be idempotent on the other side. So you're adding phenomenal amount of complexity. You have new security things you have to be concerned with, because now the service is just listing on an endpoint. Any piece of code could now go and talk to that endpoint. Here, method was only callable by the thing that was calling it, but now method is public, exposed on a network somewhere. So you might have to add authentication mechanisms for making this request. And you might want to send the data over the wire encrypted and then decrypt it on the other side. You've added so much complexity here. And then diagnostics, if something goes wrong, what if there's a network issue? How do you get performance counters or events or logs from a distributed system now with multiple machines? And even if you grab the logs and you sort them by date, the date or the clock on the multiple machines is probably not in sync. That's called clock skew. It's impossible to get multiple machines to have the exact same time on them. Practically impossible, without very expensive mechanisms to do it. So most people don't do it. Azure doesn't do it. So then trying to grab logs from multiple machines and sort them by time doesn't mean that's the actual order, because the clocks on the machines can be out of whack with each other. So why would you go through all of that pain? And the answer is because you really badly want one of these things that I talked about earlier. Right? I'm an engineer. As an engineer, I think pros and cons. So when I look at this slide here, I think, wow, there's a ton of cons that are involved in doing this. What is the pro that I'm going to get? And these are the pros. So then you have to say to yourself, how badly do you want these pros? And in many cases, you want them. I mean, these are good things to have. Independent scaling is a very nice feature to have. Using different technology stacks can be very handy thing to have. The multiple clients thing and version independently, very nice thing to have. So if you want any one of these four things, then that's going to be the cost that you're going to have to pay. And it's a high cost. So you have to really want these things badly. Okay, I've already talked about defining API contracts, and it should be explicit. They should be language agnostic. I worked on the Windows Communication Foundation team many years ago, WCF. May it rest in peace. And at the time, whatever. So at the time, we used to say to customers, you can produce your contract doing code first, or you can produce your contract using contract first and then produce the code. And we used to use that as a selling mechanism. What we were saying with code-first contracts is that you don't have to write the contract. Write the code, write your class, write your interface definition of your method and the parameters and the return values, and then we had a tool that would use reflection over that code, and then it could go and produce like a WSDL document for you, which would end up being the contract. I am now a very firm believer that code first does not work and never will. You must do a language agnostic explicit contract manually. And the typical example that kept getting us in trouble all the time was in .NET, we would have a method that took a date time. And in .NET, date time is a value type, so you could never pass null. And then we would have a guy who's writing code in Java who for the date time goes and sends us null. And when they sent us null for the date time over the wire and .NET deserialized it, it would throw an exception because you can't deserialize a null date time. And so it just wouldn't work. And there were other examples with SQL data types and things like that where it just would collapse on you. So you have to write the contract first and state explicitly what you want. All right, and then there are tools like OpenAPI and Swagger that are available for doing this sort of thing. And then use cross-language data transfer formats. Things like JSON or XML are popular. Avro is another one. Protocol buffers, flat buffers, Thrift, Bond. These are all, I mean, there's a new one every day of the week, really, of these things. So I don't have a strong opinion. I like keeping things simple and easy. And then there's always going to be a new one of these all the time. Also, consider embedding a version number in the data structure. So when it comes across the wire, you could look at the version number, and then you'd know a little bit better about how to serialize or deserialize something. Beware of leaky RPC-like abstractions. the industry sells this a lot. Once you have this contract, run it through tools, and tools will go and produce for you these RPC-like things that you can use in your code base. And then you get IntelliSense back, and you get refactoring back, and you get compile time type safety back. That's the kind of the promise of these things. And to a large extent, they do work, but there's also a lot of places where they just completely fall apart. These are also a dime a dozen. There's a new one every day. So there used to be RPC, there's RMI, there's Corba, there's DCOM, there's WCF, Google has gRPC. Right, there's a gazillion of them. There'll be a new one coming out probably in 10 minutes. There'll be one. So they change all the time. So they frequently don't work well due to the network fallacies. They assume that you're making a method call and that it's just going to work. So they don't always incorporate retries into them, or cancellation, timeout support, circuit breaker mechanisms. These are things that you would like to have control over. They tend to be chatty versus chunky. So you end up, your application ends up running slower because of that. They do offer language-specific data type conversions, but sometimes these things don't convert correctly. I gave the date-time example a moment ago between .NET and Java. They don't always work right. This RPC mechanism, how do you call a version of an API? The service offers version 1, version 2, version 3 of a particular API. The RPC mechanism is probably built to one of those, but not to different versions of those. So that becomes a challenge. How do you handle tokens that might be expiring, like OAuth tokens in there? And then what about logging mechanisms, so that when the network fails for some reason, was it the client side that had a problem? Was it the server side? Was it the endpoint that was wrong? How do you get in the middle of this stuff and try to figure out what's wrong and make it work better? So there's a bunch of issues related to it. I'm actually on a team at Microsoft now where we're trying to re-architect our Azure software development kits, and we're taking all of this stuff into account in the development kits. If you look at our new Azure Storage SDKs, they have this thing called a pipeline that has all of this stuff built into it now. And you can inject your own code in the middle of the stream. And we think this is going to make it much more effective for developers to use our services and to bug them when something doesn't go right. Yeah, something goes wrong. Okay. I've already mentioned several times that clients must retry failed network operations. This is a mandatory thing. It is not optional. And it can happen because of the network fallacies like timeout, topology changes. You should avoid sticky sessions. That affects your ability to scale. The server might throttle you. We have a bunch of services in Azure that if you're making too many requests per second, we have to throttle you down. These services are multi-tenant services, and we can't give all the processing power to you and not give it to any of the other customers. So if you're making too many requests per second, we'll start just giving you instant failures and not doing the actual work. So then you have to back off a little bit and then retry. In our SDKs, we're now building this mechanism to make it easier for you. Our old SDKs didn't do it. Our new SDKs do it a lot. Okay, and I'm trying to move quickly. So the last bullet, though, is that the client retries assume that the server handles the request idempotently. So let's talk about that, and then I'll stop after this slide. So services must implement their operations idempotently. An idempotent operation can be performed. What it means is the operation can be performed 2 or more times with no ill effect. So, for example, methods that take some input, do some processing on that input, and then return an output, these are naturally idempotent. The canonical example is add. I pass 2 variables, or x and y, 3 plus 5, let's say, to an add service. It adds 3 plus 5 and gives me back 8. If I put that in a retry loop, every time I send it 3 and 5, it always gives me back 8. So it's idempotent, and you didn't have to do anything special. You just wrote your add service to add the 2 inputs, return the result, and it is naturally idempotent. Retries work. It's great. The thumbnailing service that I've been using in some of my examples, that's naturally idempotent. If I send the service the raw photo image, and then it produces a thumbnail and sends me back the thumbnail. So I send it some input, it does some processing, it sends me some output. That is naturally idempotent. If I send it the same image 100 times, it's going to send me back the same thumbnail image 100 times. That's great. So where it becomes more problematic is you say, I need to subtract $100 from Jeff's bank account. And then something went wrong, so then I send the request and I say, I need to subtract $100 from Jeff's bank account, and then that happens twice. That would be very bad for my bank account. So there, in that kind of scenario where there's some state that's not part of the inputs or part of the outputs, right? There's the total that's in my bank account is being modified by this operation. That's where you as a software engineer have to do more work to guarantee the idempotency. And the exact way that you do that work is really dependent upon the domain, the specific scenario you're trying to solve. So one thing is a request ID could be sent in, right? So I'll just give one way of solving this problem. Is that the client generates like a GUID for a request ID. It sends that request ID to the service, and the service says, looks up in a table, have I ever processed this request ID before? No? Great. Then I will subtract the $100 from the account, and then it records it. So then if it's a retry happens, and it says, look, I see the same request ID, it says, oh wait, I did that already, I shouldn't do it again, and then it stops. Another way to do it is with optimistic concurrency pattern, if you're familiar with that. So there's a couple ways to solve this problem. They each have their pros and cons. And so how do we get exactly one semantics, which is what a lot of applications want? The client does retries, and the server side is idempotent. And that is how we get exactly one semantics in this distributed cloud computing world where we're embracing failure. All right, on that note, I will stop. I didn't have too much left to go anyway. But I think the slides are going to be available. And then my videos are on YouTube. You can watch some of it there, too. So I think I'm going to say goodbye, but I'll stay up here and answer questions, but I won't keep you from your drink or whatever they have happening that's out there. Okay? All right, thank you. Thank you.